Today we are going to be looking at section 4.2, which is all about equivalent ratios. Okay, so by the end of this section in practice, you all will be able to write equivalent ratios, write ratios in simplest form, and being able to compare them. And the good thing about this section is that we've already started to look at this a little bit even in section 4.1. So we're going to take that understanding, build on it a little bit more with some word problems and some ratio tables, okay? So when we are looking at this section, we have two new vocabulary words. The first being equivalent ratios, or ratios that are equal. And then our second vocab word, and a word that we've often discussed this year in class, is putting things into simplest form, or the smallest form of the ratio by dividing by those common factors. So we're going to do some more practice with that. In fact, our first learning objective here is refreshing our memory and how to use the greatest common factor to write ratios in simplest form. I am going to do problem 1 together with you, and then problem 2 will be one for you to do independently. So when you submit your notes to the assignment, the expectation would be that both problems 1 and 2 are completed. So let's look at problem 1 together. We have the ratio of 50 to 20. So when deciding how to simplify, to shorten the amount of simplifying steps that we have to take, we want to think about what is the greatest common factor of the two numbers given to us. If we're not able to think of that right in the beginning, we can work our way down and keep dividing until we can't anymore. But let's see if we can come up with the greatest common factor of 50 and 20. 50 and 20 can both be divided by 10. So I'm going to start there. Let me divide both of these by 10. And my new ratio becomes 5 to 2. When I think about the numbers 5 and 2, I know both of these to be prime. Prime numbers don't have any common factors besides 1. So this tells me that this ratio is now in its simplest form. So 5 to 2 would be our answer for problem 1. Now it's your turn to try out problem 2. You can pause the video and try that out for yourself. And when you submit your notes, that problem should be filled in for you. We're going to look now at Learn 2, moving on, and looking at equivalent ratios that they have the same ratio in simplest form. Okay, so in our next set of problems, our directions tell us to state whether each pair of ratios are equivalent or are equal. If we were to simplify these ratios, would they be the same? A math note for ourselves that's over here in the blue is that, again, the order of the terms in a ratio is important. So if I'm given 2 to 5, that is not the same as the ratio of 5 to 2. So let's look at the example 3. What I recommend for you guys is, when comparing two different ratios, is that we want to highlight our numbers that match up, or our terms that match up. So starting here, 7 is the first term in this ratio, and 8 is the first term in the second ratio. 8 is my second term, and 7 is my second term. I want to look at my highlighted numbers to see if they are the same. So yellow to yellow, I have 7 and 8. Those aren't the same. And pink, I have 8 and 7, and those aren't the same. So my answer for number 3 is going to be no. They are not equivalent. Not equivalent. Let's look at number 4. So my first step I want to do is to simplify if I can. So simplify first. Well, 5 is prime. 9 is not. So if I have a prime number and not a prime number, I know I'm really not going to be able to simplify anymore. So I'm going to keep 5 to 9 as is. And I want to look at 15 to 27 to see if I can simplify those, finding a common factor of 15 to 27. Well, if I think about it, I could divide both of these by 3. The new ratio that I'm going to have is 5 to 9. So I'm comparing 5 to 9 and 5 to 9. If I use my highlighter and match up my terms, I have 5 and 5, 9 and 9. I can see that those are the same or they're equal, so my answer for problem 4 is going to be yes. All right, let's look here. So again, if I can simplify first, I should do that. So I'm going to take a note for myself and say to simplify first, looking at the ratios of 12 to 13 and 24 to 39. 13 is prime. I cannot simplify this anymore, so I'm going to keep it as is. And now I'm going to look at 24 and 39 to think in my head, do they have a common factor? They do. I could divide both of these by 3 to put it into its simplest form, in which I get 8 to 13. So I'm comparing 12 to 13 and 8 to 13. If I highlight and match up my numbers, my terms, I can fully decide if they are equivalent or not. I have 12 and 8, those don't match up. 13 and 13 match up, but because this 12 and 8 doesn't match up, we're going to say this is not equivalent or not equivalent. All right, so the biggest takeaway here, and when we're given two ratios and deciding if yes or no they are equivalent, we have to remember to simplify first. Once we simplify, then we match up our terms to see if they're equal, and if so, then yes is our answer. And if they're not the same for both pairs, then they're not equivalent. Let's look at our next learn. So from here, what we're going to be looking is how to find equivalent ratios by either using multiplication or division. When given one ratio, can we come up with more equivalent ratios to it? So in this first example, our directions are to use multiplication to find 3 equivalent ratios to 2 to 3. So I'm starting with 2 to 3. And I want to use multiplication or multiply these numbers by something to come up with 3 more examples. My biggest hint to you when you're given this type of directions is we want to use these. This is, if we were to multiply this by 1, it's going to stay the same. So we don't want to use that example. Let's multiply it by 2 times 3 and times 4 to come up with new ratios. When doing that, I take 2 times 2, my first term becomes 4. 3 times 2, my second term becomes 6. And I'm going to follow that same process here with multiplying by 3 and multiplying by 4. You could pick any 3 numbers here, 2, 3, or 4. You could pick any 3 numbers. I'm just choosing that to have us go in order. But if you wanted to pick 50, or 75, anything like that, you could. You might just be working with larger numbers. So 2 times 3 gives me 6, and 3 times 3 is 9. Last but not least, I have 2 times 4 equals 8, and 3 times 4 equals 12. So I have 3 equivalent ratios here to 2 to 3 using multiplication. In the next example, I'm going to use division to find 3 equivalent fractions to 8 to 54. So same idea, the only difference now is we're looking at division. So starting with 18 to 54, maybe we want to write it like this, 18 to 54 if we're working with a fraction, maybe as a visual. Remember, we can write ratios using a fraction bar. This might help us out a little bit. So in dividing, I need to think of at least one common factor besides 1 of 18 and 54. They're both even, so that means I could divide this by 2. So let's show that I'm going to divide this by 2 and what fraction I'm going to come up with from there. I get 9. And if I take 54 divided by 2, I get 27. So that would be an example. Let's circle that one. From here, I could keep simplifying. If I'm looking at 9 and 27, well, I can come up with another one by dividing by 3, a common factor of 3, in which I get the new fraction of 3/9. That would be another equivalent ratio. And the third equivalent ratio I could come up with would be dividing by 3 again, in which I get 1/3 as being another equivalent ratio. So that is how we use division to find other equivalent fractions or ratios to the given 18 to 54 ratio. Moving on to learn 4. So, continuing with our understanding of equivalent ratios and this note of making sure that we always simplify first, we're going to be finding the missing term in our equivalent ratios. So deciding what does that missing term have to be so that they have the same value. So if I use my highlighter, I want to start by matching up my terms. So in this example, 4 is matching up with the same spot as this mystery number. And 5 matches up with the number 15. I want to find which numbers or which terms match up, or I have both of the numbers in that spot. I have 5 and I have 15. So I can think about the relationship from how do I go from 5 to 15 using either multiplication or division. We know we can take 5 times 3 to get 15. And since these are equal, that means I have to do the same to my other terms. So I'm going to take 4 times 3 to figure out my missing number. When I take 4 times 3, I get 12. And 12 would be my missing term. So this is the kind of work that I would need to see. I want to see you highlighting the matching terms and then showing either what you're multiplying by, dividing by, simplifying by, anything like that to find your missing value. Let's look at the next example. So I'm given 81 to 18 is equal to 36 to some unknown number. I'm going to highlight and match my terms. So I have 81 to 36 and 18 to some mystery number. I want to make sure that I simplify when I can. So given the ratio that has both terms complete of 81 and 18, I want to see, can I simplify this? Can I divide 81 and 18 by a common factor? The answer is yes, I can. I can divide both of these by 9 to put my ratio in its simplest form. When I do that, I get 9 to 2 is now equal to 36 to that mystery number. I'm going to highlight and match up my numbers again so that I can find my missing term. I look for which colors have both numbers there for me to work with. If I look in this example, I have 9 and 36. Both of my yellow numbers are the first terms that match up. So I want to think about, how do I go from 9 to 36? What math do I have to do if I go from 9 to 36? Either thinking multiplication or division. If I take 9 times 4, I get 36. So that means I have to do the same with my pink numbers, and that's going to help me find my missing. 2 times 4 gives me my missing number of 8 in that ratio. So 9 to 2 is equal to 36 to 8. Let's look at this next example. Let's start by highlighting our matching terms. So mystery number matches with 7, and 54 matches with 9. My 7 to 9 is my complete ratio. First, I want to see, can I simplify this ratio? Well, 7 is prime, so that means I'm not going to be able to simplify first. The next step I have to do is check to see which of my two colors, pink or yellow, has both numbers given to me. Yellow has a missing number, so that means I have to look at my pink. Let's start with the smaller number. If I go from my smaller number to my bigger number, that means I'm going to be using multiplication. So I can think about 9 times what is going to equal 54. 9 times 6 equals 54. So with my 7, I'm going to take that times 6 to get my missing value, which 7 times 6 is 42. And the last problem. Let's match up our terms here with what we have in our highlighting. We have 72 and 15. And I have 24 in my missing number. After I've highlighted, I want to see with my complete ratio, can I simplify my ratio there with 72 and 24. I can simplify this ratio, 72 to 24, in thinking about what its greatest common factor is. Between 72 and 24, my greatest common factor is actually going to be 24. So let's divide both of these by 24. I get the new ratio of 3 to 1 is now equal to 15 to my mystery number. I'm going to re-highlight and match up my terms so that now I can find my missing value. I look for which color has both numbers given to me. My yellow, I have 3 and 15. If I start at my smaller number and move to my bigger number, I can multiply. So 3 times a number gives me 15. And that's times 5. 3 times 5 gives me 15. So I need to do the same on the top here to get my mystery number, which is 1 times 5, and my mystery number is going to be 5. All right, our last learning objective here in this section is working with tables of ratios and looking at some word problems. So we're going to take what we've practiced so far with equivalent ratios and ratios in general. We're going to be looking at tables and numbers within that and solving from there. So the first example says, students in the school musical are going to sell tickets. Each student is expected to sell 3 youth tickets and 5 adult tickets. We can see that here in the first row of our table. For one student, they are expected to sell 3 youth tickets and 5 adult tickets. The students use a table to predict how many tickets will be sold. So, we have to figure out how many tickets will be sold if 50 students sell tickets. So, we're trying to figure out if the number of students is 50, what would be the number of youth tickets, and how many adult tickets would they sell. So as we look at our table, the relationship that we notice between the number of students and how we come up with our youth tickets is that for one student, they sell 3. For 2 students, they sell 6. 3 students, they sell 9. 4 students, they sell 12. So there's a pattern here. The pattern is the number of students times 3 is going to give us the number of youth tickets. So we're multiplying by 3 here. So we're taking the number of students times 3 to get the number of youth tickets. When I do that, I do 50 times 3. I'm going to get 150. So that is my answer for youth tickets. If I apply what I just thought about in the connection between for one student, the youth tickets, they sell 3, I'm multiplying by 3. In my adults column, for every student, they're going to sell 5 tickets. So 1 times 5, or the number of students times 5, is going to allow me to figure out how many adult tickets can be sold. So I'm going to multiply by 5. When I do that, I'm taking 50 times 5. I get 250. So 50 students are going to be able to sell 150 youth tickets and 250 adult tickets. So for these table types of problems, you are able to show your work just right in the table like this, filling in the blank of whichever number is missing, and we'll see how that works with our next couple of problems on this page. In the next problem, tells us that the student council is selling bouquets of daisies and tulips. The ratio of the number of daisies to the number of tulips is the same for all bouquets. You can use ratios to find the missing information in the table. So with this saying that it's the same for all bouquets, that means that we're coming up with equivalent ratios. So every ratio of comparing the number of daisies to the number of tulips, when we simplify it, would end up being the exact same. So in a problem like this, we want to find, we're going to be solving for the question mark boxes. But as a starting point, we want to look for whichever row has both daisies and tulips, the numbers given to us, which is this row. here, the 24 and 12. So for 2 bouquets, there are 24 daisies used. So let's think about if there's 24 daisies for 2 bouquets, how many daisies would be for 1 bouquet? If I was going to divide these two, I'm going to get this number. So 24 divided by 2 is going to give me my answer for the number of daisies. 24 divided by 2 is 12. Let's use that same step in figuring out the number of tulips. If there are 12 tulips that make up 2 bouquets, if I divide by 2, that's going to give me the amount of tulips for 1 bouquet, which is going to be 6. So for every bouquet, there's going to be 12 daisies and 6 tulips. We have 1 more box to fill in. If we see this pattern, I'm taking 1 times 12, 2 times 12 to get 24. So that means I need to take 3 times 12 to get my number of daisies here. And when I do that, I get 36. So now I've found all of my missing values within my table. Again, you can show your work right in the table like this, as long as I can follow your thinking, and then you're putting your answer somewhere clear that stands out. All right, last problem. Selena and Drew each have a summer job. The table shows the amount of money they earn based on the number of hours they work. So, if they work 1 day, Selena earns $31 and Drew earns $33. If they work 2 days, she's 62, he's 66, 3 days, 93, and 99. So every day, Selena's earning $31 and Drew's earning $33. So if we want to express the ratio of Selena's earnings to Drew's earnings in simplest form, we're going to look at day 1, or 1 day, to help us. That's the most simplified ratio to compare their earnings. So our ratio here would be $31. Selena is first because order matters. And Drew is going to be $33. Problem A. Looking at problem B. If Selena works 4 days, how much money will she earn? Well, as we were looking at our table, we noticed that for every day for Selena, we're multiplying the number of days by 31. So if she's going to work 4 days, I want to multiply that by 31 to figure out that in 4 days, she's going to earn a total of $124. Keeping that in mind, if you're given the next question, if Selena works 30 days, how much money will she earn? Well, we take our number of days times how much she earns per day, which is 31, to figure out that for 30 days, Selena's going to earn $930. Part C, if Drew works 4 days, how much money will he earn? So similar idea, now we're looking at Drew's amount. If we look at the table for Drew, in 1 day he earns 33. So we're going to take his number of days, which is 4, times the earnings that he makes, which is 33, to figure out his total for 4 days. And that comes out to be $132 if we multiplied it by hand or using a calculator. Last problem we're looking at now, if Drew works 30 days, how much money will he earn? We're going to take 30 days times the amount he earns per day, just 33, to get a total of $990. So if you are done with the notes, you have everything copied down, all problems should be completed. Then you can go ahead and submit this to the assignment on Schoology. Be ready to ask and answer questions in class about our newest section 4.2 about equivalent ratios.